Ever wondered why some AI models struggle to predict real-world systems, like weather, traffic, or even your phone's battery life? It's not just about having more data. The real challenge is understanding uncertainty, the hidden gaps between what we know and what we don't. Today, we're diving into the science of prediction, and why even the smartest algorithms hit limits when they don't have the full picture. Let's start with a simple idea: uncertainty. When we build models to predict outcomes, there are two types we need to watch out for. First, aleatoric uncertainty. This is the noise that's just part of the world. Think of it like static on a radio. Some randomness is unavoidable. Then there's epistemic uncertainty, which is about what the model doesn't know. It's the gap between what the model observes and the full hidden reality. Here's where things get interesting. Imagine you're trying to predict a car's fuel efficiency, but you only have partial data, like the engine type, not the exact fuel mixture. The model can't see the full picture, so its predictions become less reliable. Mathematically, this is captured by the Law of Total Variance, which breaks down prediction error into these two uncertainty types. The formula shows that when you're working with incomplete data, like partial observations of a system, the uncertainty always increases, or at best stays the same. This means even the best models are limited by the data they're given. So what does this mean for real-world systems? Think of a data center managing millions of tasks. Traditional models might look at numbers like CPU usage or memory load, but they miss the context, like why a spike happened or how different components interact. It's like trying to predict a storm by only measuring temperature, not wind patterns or humidity. The result? Predictions that are almost right, but not fully reliable. But here's the twist. Researchers are finding clever ways to account for uncertainty. By training models on raw text, like system logs, error messages, or configuration files, they're giving AI a richer language to work with. This isn't just about numbers, it's about understanding why things happen. For example, a model might see a log entry saying, "Error, CPU usage spiked at 98% due to unexpected workload," and use that context to predict future bottlenecks. It's like teaching a student to read a textbook instead of just memorizing answers. The implications are huge. When models can quantify uncertainty, they don't just give a single answer, they tell you how confident they are. This is a game changer for industries where mistakes cost millions. Imagine a self-driving car that doesn't just predict a pedestrian's path, but also says, "I'm 85% sure they'll cross here." Or a hospital system that forecasts patient influx with a margin of error, not a guess. So what's the takeaway? Prediction isn't just about data, it's about understanding the limits of that data. By embracing uncertainty and letting models learn from text, we unlock smarter, more adaptable systems. But how do we measure this progress? Ever wondered how AI systems know when they're really sure about a prediction? Or how researchers test if a model is actually learning, not just memorizing? Let's break down a key concept that's changing how we evaluate machine learning: negative log likelihood, or NLL. Think of NLL as a report card for models. It measures how confident a model is in its predictions and how accurate those predictions are. But here's the clever part. Instead of comparing models to a rigid one-size-fits-all standard, researchers use something called a recurrent language model, RLM, as a baseline. Why? Because RLMs are like shapeshifters. They can mimic almost any pattern in data. This flexibility lets scientists fairly test other models without assuming things like normal distributions, those bell curves you might remember from school. So if a model's NLL is way lower than the RLMs, it's not just guessing, it's understanding the data. And this matters because real-world problems are messy. Weather forecasts, stock markets, even your streaming services recommendations all involve uncertainty. By quantifying that uncertainty, researchers can build systems that don't just predict the future, they adapt to its surprises. But how do you test this? Let's zoom out. Imagine managing a city's food delivery network. Thousands of orders, dozens of drivers, and no 2 days are the same. That's what researchers call resource allocation in complex systems. They're using algorithms like Gaussian Process Bandit to let AI learn the best way to assign tasks, balancing speed, efficiency, and fairness. Here's the twist: they don't just rely on past data. They test models on unseen scenarios, like a sudden surge in orders or a driver getting stuck in traffic. By analyzing metrics like productivity per resource or computing power, they figure out which models handle chaos best. And guess what? The ones that track uncertainty, like when a prediction has multiple possible outcomes, tend to win. So why does this matter to you? Picture a self-driving car that doesn't just follow rules, but anticipates road hazards, or a hospital system that predicts patient surges before they happen. These tools aren't just smart, they're resilient. They thrive in the gray area between certainty and chaos. The future of AI isn't just about making better predictions. It's about building systems that understand their own limits. By combining uncertainty quantification with advanced modeling techniques, we're not just solving problems, we're preparing for the unexpected. Thanks for watching and stay curious.